Hello guys, Cyprien here from FE4, and in today's tutorial we'll talk about a plate with a hole. So it's a very classic example, and you see that I prepared a lot of stuff for you, so I try to make it as interesting as possible, and I am going to talk about a lot of things today. So the first thing obviously will be how do you build this model in Aster. And you'll see that I will use not the traditional method step by step to build all the commands. I'll show you a much faster and easier way by using the assistant. So it's something I've never talked about in my previous video, but you can actually generate this kind of simulation very easily using the assistant function you have in Aster. So I'm going to show you how that works. We'll have also a discussion about the difference between the result of first order and second order, and why you have different in accuracy and all of that. We're going to talk about the difference between a different type of loadings, because I had some people contacting me telling me that they're not getting the right results, and after checking it's simply because the loadings are wrongly applied. So I'm going to talk about this so you don't make the same errors between pressure, force, nodal forces and all this, and this is very important to understand. So we'll talk about this. Finally, but this is actually also very important, is we'll do a small mesh convergence analysis, and we will automate together this process using YACS. So YACS is a module like that allows you to put some Python function into it to create some small automations, and this automation will generate the mesh with the right mesh size, and it will calculate with Aster, and then it will give you results, and then at the end we will generate this mesh convergence graph at different mesh size. So I'm going to show you how to do that with Python and Jupyter Notebook. So this video is packed with really amazing knowledge. So I hope that if you like it and if this is useful for you, please subscribe to my channel, give it a like. It took me a lot of time to prepare all this, and I really hope that this will help you in your engineering career. So thank you so much, and let's go together to start this tutorial. So this plate with a hole analysis is an article that I published on the blog a few years ago, and this is something I always come back to, because if you want to be good in FEA, you always have to have a few sample simulation or you can call that test simulations, that you know very well what is the answer to those simulations. So it can be this plate with a hole, it can be a simple beam analysis. There are various kind of tests that you can do, and what is really useful about this is that we know the theoretical result of this model. So it's a very simple model. At the basis it's a plate like that with a hole at the middle, and in practice it's divided in four, so we're only studying a fourth of this model. So there are two symmetry conditions on both sides, and there is a force applied here on the right. So this is a pressure, and by the way, this is something I'll come back after because it's important. Make sure that, you know, even if it's written F, if the unit is Newton per something, per millimeter, per surface, or per unit of length, this is not a force, this is a pressure. So be careful when you look at that. This will be important when you assign the type of loading that. So we'll talk about that a bit later in the example. So this plate is very useful because it allows us to also study the convergence of different types of elements. We know that the von Mises stress at this point here should be 372.7 MPa. So this is some kind of theoretical value, and this is used to kind of assess what is the accuracy of your current simulation. And it's very interesting because you can test with various element sizes, and you can see what is the convergence, the rate of the solution according to the mesh size. for first order, for second order elements. So and this is also a good discussion to talk about the difference between first order and second order, or with quad. So this is the result I found like a few years ago using another software called Midas NFX, and you could see at that time that the convergence rate for the element size for the first order was very slow compared to second order and quad. So now I'd like to reproduce the same thing, but with Salome Meca and Aster as the solver. So the purpose of this video will be to show you how to set up this model in Salome Meca and how to perform this analysis. Let's start by opening Salome Meca. So I'm on Linux Ubuntu 18.04 and I'm using the version 2 from 2019. So it's not the latest, but it should be very close to the latest in terms of the steps to do the simulation. So the first thing to do is to create this plate. So let's go into the geometry module. And so there are several ways to create these plates. I'll go for, let's say, the way I think is the simplest is to create a rectangular face first. So let's create this. And I will be working in the millimeter unit. So that's why I'm leaving it like that in hundreds units. This is millimeter. This will be important when I define the material characteristics. So my plate is here and it's centered at the middle, so I want to move that. So let's go to transformation and let's translate this. So in X direction I have to move it 25 and 50 in this direction, and uncheck the option create a copy, otherwise it will copy your model. Now let's create the hole. So I'll have to create a disk of 20 millimeter here for the ray. Okay, and then I'll just cut. So Boolean cut operation. So let's select the main object as the face, the tool object as the disk. Yeah, and now I have my plate with a hole. So pretty simple, right? Now what I have to do is to define the groups that I will be using for the simulation. So let's create the groups. So those are edge groups, selecting the main shape. Yeah, so make sure the main shape is selected here and the name of your main shape is written. If it's not, just click here and select the shape like I did. Now once you do that, if you are in edge mode, it should change into showing you lines like that. So click on the line here, click on add to add it here, and I'll change the name and call that edge X as the name. So that's my first group. Second will be this edge here. Y, and there will be this will be the load edge. Okay. Now one thing I must say also is that one thing you can do if you really want to study this example, the best possible way is to really cut the model in special ways to create a very good mesh of that. I will not play this into this tutorial. I will let you experiment with this. I will only show you how to simulate the simple plate and mesh it with full tetra, and then you can play with options like meshing it smaller around the edge and all of that, or meshing it totally with quad, or all these things. You can try it out. Now what now that I have this geometry with this, let's rename a bit that. Let's call that plate hole, like this. Okay, so I have this plate, I have the geometry done. Now let's go to the next step, which is the meshing. And let me show you how to mesh it. It's pretty simple to mesh actually. So I will create the mesh, choose NetGen 1D, 2D, and I will use the NetGen 2D parameters here. So I'm really using the most simplest setting to mesh this. And I will use first order, so I'm not checking the second order here, but I'll show you later on how to change from the first order to second order, and I'll show you also what is the difference. So we'll see that later on in this video, or maybe I'll make a separate video because this is pretty interesting to study. Okay, so you have this mesh, let's compute that. So I have 264 elements, and let's create the groups from geometry. So create the mesh groups, and let's create the node groups at the same time. I don't think I will need node groups, but maybe I will, just to show you a bit, but not necessarily, but I'll create them. Okay. Yeah, and why not showing you right away how you can change that to second order, because it's pretty easy, but not everyone knows that. So select the mesh. If you want to, let's say you have already created this mesh and you want to go to second order, you can click on modification here, and you have an option called convert to from quadratic. So you can use that. Click and select convert to quadratic, apply, and your mesh will become quadratic. Now what you have to be careful if you do this is that you have to delete all the groups here and recreate again the mesh groups. If you don't, you know, the IDs of the elements stored into those groups will only be the ID of the first order nodes, and you will miss the IDs of the second order nodes. So if you have already the simulation set up and everything, and you're running this plate, and you say, oh, I want to come back and change it into a second order, then you will have some surprise in the result, because you know the loads will be very weird, and that's generally because you forgot to recreate the groups. So just, you know, that's just a side notice, because this is something that might happen. Okay, so I created the mesh. Let's save my so let's call that plate hole 2. Okay, always save it, you never know what can happen. And let's export it at the same time. So let's call that, I don't know, plate hole 2. Okay, and the mesh is now down, so now we can go to the next step, which is the code Aster. So let's go to Aster study. Okay, and instead of showing you all the process from zero and, you know, reading the mesh, reading materials, assigning everything, I have several videos on YouTube showing you how to do this from zero. Instead, I'll show you something much easier that I've never showed in any of my videos, but once you know this trick, you'll always use this option. There is an assistant in Aster Study, so you can right-click, add a stage with assistant, and you see you have actually a few types of simulation which are already predefined for you. So if you select isotropic linear elasticity, it will actually guide you through the definition of the commands that you have to have for the simulation. So it's very, very useful. And you see this will be very quick. So I'll use the mesh I just created. This will be a 2D analysis. So you have between C-plane, D-plane axis. So C-plan, D-plan, I think this is plane, I don't remember if this is plane stress or plane strain. I'll have to check later. So I use the C-plan, so let's say this is plane strain maybe. Now you have to define the material properties. So here, remember that I use millimeter as the unit, so that's where you should be careful. And the Young's modulus should be 210,000 if you are in millimeter units, and the Poisson's ratio is unitless, so it's always stay the same. Now it asks you for the degrees of freedom. So here, click here, select the edge X. Now if you remember, the edge X is the one on situated on the X axis. So what I want is that my model can slide on X, but it cannot slide on the Y axis. So what I have to do is to basically block the degree of freedom on the Y axis and leave the other degrees of freedom available. And for the edge Y, I block the degree of freedom on X axis, and I leave the dy axis free. Now, because this is 2D analysis, there will be no dz degree of freedom, so I don't need to block this one. And now the pressure load, so select the load edge, and the pressure will be equal to -100 Newton per millimeter square. Well, here it's a 2D, so per millimeter. Now select the result output file. So here, instead of just entering a name, it's good to click on browse and then enter here the name of your result. So let's call that plate hole res.rmed, for example. And you see the full path will appear here. Finish. And here you got all the steps of this analysis. So now you don't see the model appear, so let's double click on read a mesh and you see that it will appear in the view. And basically everything is defined, well, almost. So by default, what does it do? What does this assistant do? You can have a look at that. It reads the mesh, it assigns a finite element model, it defines the material, it assigns the material, it assigns the boundary condition, it assigns the loads, and then it assigns the analysis and your results. Now there are a few things that it doesn't do. So it doesn't calculate, for example, volumetric stress. So for example, forces or reactions. So I need to add a calc champ to this. Don't forget to check this option, reuse the input object, so that to keep the same name between those two. That's important. And here I want, so volumetric is stored under critères. So in French it's criteria. It's and sigma equivalent elga, sigma equivalent L no, so element goes point element node, and sigma equivalent node. Okay, I got those three, and I want to have the forces as well. So the reaction forces calculated. You'll see that this will be useful to understand what is the force applied to our model. Okay, so I got all of this. Click on OK. And there's one more thing I may need to do, because if I solve like that, it might fail. And this is, I need to add something here called the orientation of this edge. So when you apply pressure to an edge, you need to apply an orientation to this. So I think it's this option, orientation PO 2D. Anyway, if you don't do it when you solve, you'll have a red sign. It will tell you that you're lacking this. So generally, that's how you know about it. So click on the load edge, and that's basically all you need to give it. You need to give it the elements of this. Okay. And once you add that, it should recognize this edge orientation, and what it does is basically it orients all the elements from that edge in the same direction, so that it can apply the pressure. Okay, and I think we're ready to solve that. Okay, so let's go to history view. Click on my current case to add it. The run button become active. Make sure the time here is set up to a long time, like 15 minutes is okay for this model. In case you have 1 minute or something, that you have to increase it, obviously. Also check your memory is enough. Here I have 2 GB assigned, so it's enough. Let's just run that. Okay, I need to save the study. And there's one more thing you need to do, activate the auto refresh and put it to 5 seconds. Otherwise, it will run and it will not refresh, so you'll find it's a bit annoying. So you have to auto refresh in order to see the results coming in. So let's wait, should be very quick. Okay, got it. So it's green, it means that it worked. Now let's review the results. So in this version of Salome, I can use this post-process option. If you have an older version, you'll have to go into Paravis and look at and open this Hermit file. I'll probably do that also a bit later in the video, but right now let's open quickly this with this let's say new post-processor, which is not really new, but it's pretty cool actually. It makes things much easier than before. So I like that they have developed this this simpler post-processing. Okay, and this is what you get for your plate. So this is the deformed shape, magnitude, and let's look at the equivalent stress. And now we see that the interpolated equivalent stress at this node should be the maximum. It's around 320. So it's not, it's still pretty far from the 372 MPa that is the theoretical result. And of course, that's because this plate is very coarse, so the mesh is much too coarse for that, and also because it's a first order elements. And no, the plate on the left is first order element, and the plate on the right is second order element. So if you look at the classic kind of result that you get out of any simulation software, you'll get the von Mises stress, which is averaged at the nodes. So in code Aster, this is called sig neu. So this is it's the shortcut for stress, equivalent stress at the node, basically. And then you can choose the type of stress you want to look at, which is the von Mises. And if I use the probe here, so I click the small icon and I activate the results SCAQL no in the selection display inspector. By the way, if you don't have the selection display, just activate it in the view here. And I go over the mesh like that, I can see the results. So you have a bunch of numbers here. The only one you have to look at is the first one. The reason is that this stress is given at the element, so it's a surfacing type of result, but it's average at the nodes, and the probe here in ParaView is only allowing me to view the result like that at the nodes. So the first result is the von Mises, the second is Tresca, so we don't care about the second and the others, just the first one. So if we look at the results here, and especially the stress result at the step here, so the actual theoretical result you should get is 372 MPa. So we see that for the first order we get 320 MPa, and if I look at the second order result here, so we get 379, so much closer to the actual theoretical result. So it's almost good, right? And the mesh size is similar, so we have a huge difference between the result on those two. And it's not a secret that second order are much more accurate than the first order, but most people don't understand why. And in order to understand why, you have to look at the stress which is actually calculated of the elements, not the average stress at the node. And to do that, so you have to first activate the filter here in mechanics, no fill to surface. So once you activate this filter, you'll see this result appearing here. And instead of looking at this, we will be looking at stress equivalent at element node, no, here. So this is for this one, and I click on this window here, and now we see the result is much more different, right? So here we see a major difference is that the actual value of the von Mises stress is constant per element. So here you have one value, you have a second value, and this is really what it is. The first order gives you a constant stress value per element. And if we look at the result of the second order, so this is linear result. So you have a gradation already available of the stress, a linear value of the stress within the element. So by the way, we see the middle node here. And the second thing we can see here is that the approximation of the whole shape is much more accurate in second order, because this middle node is getting closer to the circle. So it's deforming my triangle here so that it goes closer to the circle shape. While in here, of course, there's no middle node, so it's not possible to approximate the circle shape. So there is this problem here. The elements are too stiff to actually approximate correctly the element shape. And the second problem is that this is constant value, this is linear value. So so you see the value here. If we look at the value at the element value, so this is 158, this is 260, this is 780, and if we look at the value here, well, we get a value of 131 and 162 and 220, so that's very different. So before we go to the next part, I'd like to talk a bit about boundary condition, and especially the loading of the plate to this edge here. Because last week I had someone contacting me, tell me, okay, Cyprien, I tried your tutorial, your analysis. I'm doing a simple beam analysis and I just can't get the theoretical results that I'm supposed to get. I used the right material, I did the calculation, and whatever I do, I never get the right results. So he just sent me his model. I had a look, and the model was okay, except one thing. The boundary condition here was wrongly set up. And this is a very classic mistake. So that's something I'm going to talk briefly to explain to you how this works. Because a lot of you probably don't understand this, even if this is very basic stuff. So you saw how I assigned the pressure to this load. I used, because this is a pressure load, I used this function press rep. So it means basically pressure distribution. So it means that I am applying a pressure distribution to a certain geometrical shape. So I'm putting 100 Newton per millimeter on this edge. Now there are some people who will think that, okay, there are other types of loading, or maybe by mistake they don't know press rep is the right one. So they will think, okay, I want to assign a force, let's say, of 5,000 Newton to this edge. So because this is a force, it's not a pressure, so I will use force, maybe this one, force nodal, and or there is also force face, but in the 2D case this doesn't work. So I'll show you the example with force nodal. So what they believe is that if you want to assign a total force of 5,000 Newton, you just choose force nodal, and then you just select all the nodes here, and well, it should work like you want, right? It should do a 5,000 Newton force to this edge if you select all the nodes. Well, it doesn't quite work like that, and let me show you why with simple calculation and the results on this model. So I use a press rep, right? I have pressure applied on this node. So let's have a look at the result that I got. So let's go into Paravis, let's activate the visualization of the results, and if you remember, I have calculated the force. So force noda is the nodal force at those nodes. So activate the interactive selection of the points, select result force noda in the selection display inspector, and you will be able to view actually what is the value of the force at those nodes. And what do you see here? You see that the value in the y direction of the force at this node is not 100 Newton, right? It's 625 Newton. So if I apply a pressure of 100 Newton, I'm getting 625 Newton on each of those nodes. Why that? So first of all, let's do a very quick calculation. So what I applied here is a pressure. So I applied 100 Newton per millimeter, and the per millimeter is very important. So let's say that you understand that this is a pressure. So how do you convert that into a force? You basically multiply by the length of this edge, right? So this is 50 millimeter. So you get a force of 5,000 Newton. So up to here, everything is fine. So why do I get 625 Newton? Because I have 1, 2, 3, 4, 5, 6, 7, 8 elements here. So if you think that the total force applied to this edge is 5,000 Newton, you divide that by the number of elements and you get 625 per edge. Now, one interesting thing is that the value at the nodes here is 625, but if you look at the corner nodes here, it's 312.5 and 312.5. So why is that? It's because the pressure you apply to the edge here is basically the value of this force is divided between the two nodes on those sides. So each of those nodes gets half of the value of this pressure, so 312.5. But because there are two elements here and they both have a node in common, basically this node gets 312.5 Newton from each side, so it basically is loaded as 625 Newton. But the node at the corner, it only gets once this pressure, so that's why it's loaded as 312.5. So what you see here is that if you apply a force of 5,000 Newton, you actually are applying, let's say, around 625 per node, except the nodes at the corners. So if you want to use this function force nodal, like I did here, like I was showing you, if you want to use force nodal, where is it? Here, yeah. You want to use this and get the same result as the press rep. So what you should do is basically select the nodes here inside and assign a force of 625, and then you should separately select those two nodes and assign a force of 312.5 Newton. So that's the only way to get the same result as the press rep. So you cannot just select all the nodes here and say, okay, this is the force, so total value of the force is 5,000, so I'll just apply 5,000 to all the nodes and it should be working. No, it doesn't work like that. So now I hope that, you know, by doing this, you will not do the same mistake. So be careful about this force nodal and this press rep. The easiest way, obviously, to assign this is always to assign a pressure rather than using a force. But, you know, in some cases, you want to assign a force to the nodes. Or if you are in 3D, you can use force per face. So if you use this force per face, you can select the face and assign directly 5,000 Newton. So in this way, it should work, right? So, but, you know, make sure you understand the difference between force nodal, force face, a press rep, and, well, you have other types of forces as well. So I will not detail that anymore. So that's just a side note. So and I hope this is useful. So let's go to the next part of this tutorial. Okay, so now let's take all what we've learned and let's automate all of this. So the purpose will be to be able to generate 1, 2, 3, 5, 6 different mesh with different sizes, and to draw automatically the mesh convergence graph showing us the maximum form meter stress in function of the mesh size. So the first thing I'll do is that I will export the result into a text file. That will be much easier to process than the current AirMed result that I'm getting out of this model. So I'll modify quickly the Aster case study, and I will add a second type of output. So let's go back the case view and let's add another set output result command, and let's call that, or maybe let's choose the format first. So format result will be in text file, so that's the one I'm looking for. So select result format, and let's call this file plate whole dot Rusu, like that. Okay, you can call it whatever you want. And I have to assign some results to this. So let's assign the basic result of the simulation. And you can filter out the results which are printed to this file. So because I'm not interested in putting all the result into this file, I'm only interested in getting the form meter stress into it. So I have to activate basically the field that I want to export. So this will be this one, non-champ. So this is the name of the field that I want to extract from this. And if you remember, the form meter is stored into S sigma equivalent node. So that's the field I want, and I want to extract the maximum value, which will always be in this point, so that's convenient. Yes, okay, just validate that. Let's test that it works. So let's run again this case. Okay. Okay, so it run. You see I have another type of file that has appeared here. So let's have a look at this file. So it's this one, plate all. Let's open it. And you see that I'm getting the maximum form meter stress So I'm getting at the same time all the Tresca, the principal stress and everything. I only care about this. So I'll have to use some kind of script to extract this value here. We'll see how to do that a bit later. But basically this is what I want, so that's good. Okay, so now let's see how to automate all this. So to automate this, I will use the module called YACS. So I have already done some videos about the YACS module on YouTube. This won't be a full introduction to YACS. If you really want to know how it works in detail, go and watch those videos. I have like 5 videos, I think, which really go into the whole details. So this one will be, let's say, easier. So what I have to do is to create a new YACS scheme here. Let's create a node, inline script node, and I'll have to put some code into this node. So let's just change them. Let's say model generation. So this will be the name of this node. So what code should I add here? Let's go back to my, well, actually I can dump the study here too. So this is important that you dump the study just after you build this model, because if you kind of save and reload, I'm not sure you will get the same code. So let's save this. Let's call that dumped study, for example. So this will dump a Python file. Now let's open this file. So this is what I'm getting out of this, and you really have all the steps of building the plate, creating the groups, creating the study. You have actually much more than I really want, because this is all the post-processing and all of this. So what I'll do is that I will take let's say up to the SMesh component, and from the beginning, from import sys, I'll copy that, and I will copy that and paste that here, apply. And what I'll do is that you have to find the parameters that control the size of the mesh, basically, because this is what I want to play with. And this parameter is here. You see I have a 6, which was the mesh size I input. So let's go in this model general and let's put double input variable. And this will be called mesh size. Okay. So I have to initialize them because I have only one run, so we'll test if that works first. Let's put 3 as the mesh size here, and let's modify this code. And now that I have this input variable, I can replace the 6 here by this variable mesh size. Apply. Also, let's change the name of the file generated. Well, it should generate a file because I think it will export, but it will also generate the file directly into your SMesh module. So let's run that. Let's go and prepare the current edit for the run. Okay, let's click on this start, and it's done, so it should be working. So now if I go back to the SMesh module, you see I have a second mesh available, so let's show it, and you see the mesh size is much smaller. So I've succeeded to automate the creation by just changing one parameter. So also don't forget to save your scheme. The saving of the scheme comes separately from the HDF file of Salome. So you have to click on the icon which is below the save document icon, and it will tell you save the current YACS scheme. And this will be saved as an XML file which contain this running scheme, and it will save everything, the Python code. So now that we have this node that can generate the model and mesh it at the right size, the next step is to add a node that can compute all of this and provide the result with CodeAster. So let's create that node. Let's create an inline script node. Let's call that the Aster node. And the problem here is what is the kind of code that we'll put into here. So I have already talked about that in my previous video on YACS. So what you have to do is to do the following. First of all, this is the code to put into this. So because CodeAster does not, and especially the Aster study module does not have a Python API like the GeoML or the SMesh module, the only way for us to launch CodeAster with the mesh that we generated is to use a subprocess. So it's a Python way that will allow you basically to call any executable on your computer and to just launch it for you. So it's some kind of small application launcher in Python basically. So if you look at this code, what I'm giving it is an export file, and then I give it the path to my CodeAster executable on my computer, and then I give it, I launch this using the subprocess command here. So the only thing you have to change from this code is the path to your folder where you have actually put the export file, and you have to change the path to your Aster executable. So as you see, generally the Aster executable is located into Salome Meca, then you have a v something folder, and you have tools, and then you have CodeAster front end bin, and your executable as run should be inside this folder. So let's take this and let's paste that into my node. And the next step is to set up this export file, right? Because right now, so I cleaned up a bit my project here. I had a lot of previous files from the other analysis, so I just removed that, and now I have only the files that I just generated in this tutorial. So what I have to do is to go into the files that I generated through my previous CodeAster study with Aster study, and they are stored into this folder. So I have the first run case, the second run case, result stage, and you see that here I'm finding this export file. I have the com file, I have the met file. So, and basically the com file and the met file are all linked into this export file. So the export file gives you all the files that will be used to compute, and it gives the numbers and the units and all of this. So what you need to do is to take this export file, take this com file, and that's all. Basically the other will be generated automatically, and we will replace the met file. So copy that into your main folder, paste this, and you need to modify the export to basically give it the right links to all those files. So my folder here, the path to my folder is the following, so I'm just copying that. And what I have to do is to basically put that here. So this one, this one, this one, and this one, and this one, and the last one I don't think I need that, I just remove this. And I have to change the name of the met file. So the met file generated by this previous step is called platehole2. So I have to input platehole2 here. I save this, and all of this basically are some kind of settings and variables that I don't really need to change. Well, except if you want to change the memory or stuff like this. Here should be okay. So I just, so now that I have this node, I need to launch it. So I will link the out of this node to the in of this node. Let's save my scheme, and let's try to run that. So let's prepare the current scheme, and let's launch it. So now Aster is activated, and now it went from blue to green, so it means that this is done. I can check if that worked by looking at the container log, and the end tell me that I have exit code 0, which means that everything went according to plan. So that's good. So now if I go into my folder, I see that I have those files that have been generated, which are basically my results. So my results have been generated by this this code. Well, that's great. That's exactly what I want. And now I can basically change the size and every time recompute everything and get the results. So now I need to put everything on that into a for loop that will generate recursively different mesh size. So let's create this for loop by putting a new node into this. So, okay. Yeah, every time I forget this, there is the execution view. So if you are in this view with the small gear here, close that first, and now I'm in the edit view where I can add again the node. So yeah, don't remember every time I forget that I have to close this window. So now I can create a node, and I have several for loops available. For each loop, let's create a for each loop, and I have to think about what will be the input to my loop. So my input will be some an array of doubles. So basically I want to give it a sec, maybe sec maybe doubles should work. Double. Okay, so here's what I'm doing here. So there is my for loop, there is my two nodes. Now I need to put that into the for loop. So to do this, I have to select those two nodes. Yeah, actually what I have to do is to create a container, a block node. Then I'll delete this link. So the way YACS works is not very intuitive. So I have to cut that, and I have to paste that into here. So now I have this node inside the block. I have to cut that, and I have to paste that into here. I have to relink them again, and I have to cut the block and paste that into this node. So now I'm getting this block into this node, so it will be generated at each time. Now I need to give it a sample collection. So the input of this node will be input data node. So I need to give it input data here, and my input data will be a sec double. So a sequence of double. So what I need to do is to so this will be my mesh size array, so I can call it like this. I have to initialize it with an array of value of all the mesh size I want to generate. So let's say 1, 2, 3, 4, 5, 6. Yeah, I think that will be fine to start with. So this is initialized to this, and now I have to give that to my sample collection and link those two nodes together. So what this means is basically you generate the input data here and you give it to your for loop that will be stored into a collection, and each element of this collection will be iterated and stored into an eval sample at every loop. So now I have to take this eval sample and link that to my mesh size, which so every iteration of the loop I will get a new mesh size generated. So in order that works, let's try to launch that. So let's save this first. Let's open the execution view and let's start. And now you see the first iteration of the loop, second, third. I don't get any errors, so it seems to be working. Yeah, and I didn't get any error, everything is done. Now if I look at my results, the problem is that those results, there's basically only one result, which is the last one, because they all have the same name. So what I have to do is to rewrite the name of the file after each calculation with code Aster, otherwise each previous calculation is just overwritten. So let's do that. So in order to change the results, what I can do is copy the result generated and change the name at the same time. So let's add a new node. So that will be an inline script node again. Let's call that copy res node, because it will copy the results. And the script I have to use here is I will import the shuttle module, which is the one to use to copy a file in Python. So shuttle.copy file, and here I just need to give it the path of the file I want to copy and then the result. So the path of the file to copy is the one written in this export file. So it's the text file containing the results. So it's this. So don't forget the brackets here, and the name of the resulting file here. So for the moment I just put the same name, but I need to change this name, right? And I need to change this name according to the result generated, so I need to put some kind of variable here. So to do that, so let's first link the output to this. To do that, I have to add an input port. So this will be a double, and this will be the same as this one, mesh size. So let's call that mesh size again. Okay, and I will link this eval sample to this. So this value mesh size will take the same value as here. And now I can access this mesh size variable within this file. So what I do is just put a double bracket plus, like that, to concatenate. And this variable I'm getting is a double, so I need to convert that into a string in order to concatenate it. So mesh size, apply. And with that, I should be done. So let's run this, and let's hope it works. So this time again it computes the results, but if you look at the result generated, you see that I have plate 3, plate 4.resu generated plate 5, plate 6. So that's what I wanted. So I'm getting the result for each step of the simulation. So if I look at the result for 1 millimeter, you see that I get the von Mises value of 3.71, which is very close to the exact value. And if I look at 2mm, it's a bit less accurate, 3.64, etc. up to plate 6. Okay, so we're almost done. Now the next step of this tutorial will be how do I take the info into those text files and generate a curve with this. So for the last phase of this tutorial, I will be using Python and Jupyter Notebook to process the data out of those text files. So if you're not familiar with Python and never heard about Jupyter, well, that part might be a bit difficult for you to understand. So I'll provide the script, so don't worry about that. You can just take the script, run it, and it should work. Now, if you want to learn more about Python, I'm also giving Python course through my newsletter on FE4. So if you're in the newsletter, you'll probably know about this, or you can contact me if you're interested to join this course. Okay, so now I won't go exactly into the detail on how I generated this script, but it just took me 30 minutes basically to find out how to build this script to process this data coming out of those text files. So what I did is that I went into this folder where I have the results. Then I import the various Python modules that I need, OS, system, and regex. Then what I do is that I use the OS walk function to open all the files into my folder, and I filter the file by the extension of the file. So I just want to keep the Rusu file, and also I want the Rusu which have the value of the mesh size after that, because that's the kind of convention that I took. So as you see, after executing this, this is what it can find in the directory. Now, what I did after that is that I opened each of those text files and I extracted the value of the maximum von Mises stress. So that's probably the most difficult part of the script, is the regex. Regex are really useful. It's not very intuitive at first if you never used regex in Python. But I can tell you that using regex, you can basically extract any type of information from any type of text file. So it's absolutely awesome thing. Now it's a bit complex to set up this value here to extract the right value from a text file. So for the moment, just take this one. And this value, what it does is that it basically opens this. It takes this line here and it says, okay, I'm only interested to look at this value here. So that's what I want to extract. And that's why there are some parentheses here. So the value in between the parentheses is the number that I'm basically extracting out of the text file. So this value, I store it in this variable mo2. And now what I did also is that this mo value is basically this number. The mesh size itself will be stored into the mo value. And I'm putting that into an array, and I'm converting also the string extracted into a float. So basically what this code does is that it takes all the files which are in this format, it extracts the von Mises value and the mesh size, and it basically gives you this as a result. So that's a list of lists with the mesh size and the value of von Mises stress. Now there's a small problem, is that it's not in the right order. So I want to classify that in the right order. And to do this, I am using this function here. So again, you can just search in Google how to sort a list of lists, and from the first element, and this is what you will find. So I basically copy pasted what I found. And this allows me to get a list of lists, which is sorted this time. Then I extract it into two arrays, the mesh size and the von Mises, which will be useful to plot that. And to give you an example, this is what I get for the first font messes maximum. So I get a list of all the font messes values. Then I can use matplotlib to plot that as a graph and save the figure under this name. And this is what I get basically. This is the graph of the convergence. And you see that when the mesh size increases, well, the value of the maximum font mesh stress decreases. Now what is funny is that on this graph I have some kind of anomaly at 5mm. So it's almost a line, but at 5mm it just went way down. And I don't know why. I suppose that because there is some kind of averaging between the nodes going on. So when your mesh is high, basically, you can't really predict, you know, that the value will be constant. So maybe, you know, there is some kind of anomaly here. But basically, you get the idea. You get your mesh convergence graph from. So that was the goal of the simulation. And now you can go back to your scheme. So you can put this the script that I put into another node and run that. So now it should be working theoretically, but I don't know why the script at the end, the matplotlib part actually doesn't seem to work. It causes an error. So I believe it's a bug of YACS probably, or the Python distribution of YACS, which I don't know what cannot save figures or stuff like this. So so basically what you can do is just run this separately as a simple Python script. So you do not put this into YACS, just run it outside of YACS like I did. So you can run it from terminal or run it from Jupyter like I did. And after that, so I'll just I'll try to see if I can find another way to plot the graph out of a node. If I cannot, then I'll just do that. I run it separately. It's not a big hassle to just separate Python script and run it after you run all that in YACS. It doesn't have to be everything in YACS. Now, the other thing you need to, if you want to get more data points, is to modify the array here, run again the script. It will generate all the results, and run again the Python script to generate the picture, and you get your small automation. So I am conscious that this last part was a bit fast if you don't know about Python, but like I said, I will provide the script, so you can look at that at your own rhythm. And if you have any questions, as usual, just let me know, put a comment. I'm always you know, happy to make a separate video or something about one of those things you want to study more in detail. And yeah, that's it for this video. So now you know how to automate the creation and make some nice mesh convergence plots. And I hope it was useful. So at least I hope you learned a lot of things out of this. So thank you very much for watching, and see you in the next videos.